As I was saying, can everyone hear me now? Perfect. So if anyone is having connection issues, we are also live streaming the presentations to YouTube. So if you check the chat, you can find the link there if you're having issues. So here with me, I have Ben Ferrar from Carpenter. Ben Ferrar was appointed Vice President and General Manager of Carpenter Additive in April 2019. In this role, he was responsible for the overall strategic leadership and operational execution of the Carpenter Additive business unit, a vertically integrated additive manufacturing partner providing complete end-to-end solutions to accelerate materials innovation and streamline parts production. Ben is driving Carpenter Additive's global commercial strategy and delivering innovation solutions to facilitate AM industrialization. All right, I will go ahead and mute myself.
Before you mute yourself, can you see my screen? Because now I can just see the presentation. I can't see myself or you.
Yes, we can see your screen, and if anyone's watching, they can also expand the screen by clicking the arrows in the top right corner of the shared screen.
Okay, brilliant.
Awesome. Well, thank you.
Well, thanks very much for the introduction. Firstly, can I say, wow, right? This is the first time I've done one of these virtual conferences, and I'm really impressed with what you guys have done. It's really impressive to see at such a tough time people being innovative and people looking new ways to get business done. So congratulations to the team. So today I'm going to talk a bit about Carpenter technology and give you a bit of an overview and talk about our additive business unit. I'll also talk a bit about some of the challenges that we face with additive manufacturing in terms of materials development. So I'm going to talk a bit about degradation, focusing mainly on Ti-64, and then I'm going to move on and talk about some of the material developments that we've done with Ti-64, specifically related to our e-beam manufacturing capability, and I'll give you a bit of an insight into the future and where we're going with that as well. So for those that you don't know, Carpenter Technology is a 130-year-old specialty alloys business, so approximately $2.2 billion in sales. And we have a number of product forms. So we supply ingot and billet and strip and wire. And some of our newer product forms are powders and components and additive components. Okay. We operate in 7 strategic markets that you can see there in the middle of the screen. And I'll talk a bit about on the next slide about how much of our business is in each of those areas. And you can see our sort of full range of alloy portfolios on the right-hand side of the screen. But ultimately, what this translates to is thousands of customers and hundreds of high-performance alloy grades. So when we look at our material solutions across the different business segments that we supply into, over 50% of what we do is in aerospace and defense. And then our second sizable market is industrial and consumer, followed by all transportation, medical, energy, and distribution, sharing about between 6 and 8% of our sales. So the majority of what we do is really on the high quality end, and this is why additive fits so well into our product set. So if we move to Carpenter Additive, then our mission of Carpenter Additive, and a number of years ago I wasn't with Carpenter when the initial vision started, but really the CEO, Tony Tane, had a vision to be able to provide a solution to a customer no matter where they are in their journey, and have a team of highly trained, experienced engineers to partner and ensure our customers successfully advance their additive manufacturing process or program. And I'll explain what I mean when I talk about that as we go through the presentation. So if we look at how Carpenter Additive is built up, so culminating in the formation of Carpenter Additive in May 2019, it really started out, and the knowledge started to build in the late 80s and early 90s with start in gas atomization of metal powders. And then throughout the late 90s and late 90s and the 2000s, really through acquisition, powder manufacturing capability was brought into the Carpenter Technology Group. And so We have a facility in Bridgeville, Pittsburgh, in Sweden, and in Rhode Island, which all have high quality gas atomization capability. And at this point in time, they weren't really focused at additive manufacturing. It's that later on that developed into the strategy. So then if we come into the more recent years, okay, in around 2012, we commissioned the building of a new superalloy gas atomization facility in Athens, Alabama. We acquired Puris, which is a titanium powder manufacturer. We acquired Calram, which is a part manufacturer, and LPW Technology. Okay, and what we've done now in the last 12 months is we've put all of these assets, or a combination of these assets, under and knowledge under one business unit and under the name of Carpenter Additive. So it really is a milestone moment in terms of, you know, innovation in powder and AM technology. So if you look at, when I talked about being a partner on the journey, on our customers' journeys, you know, there's a huge number of steps that have to be completed to build a sustainable AM program, right, of scale in a complex industry like aerospace. You know, firstly, we have to be thinking about, you know, defining the aspiration and setting the target. We have to organize the, you know, a customer would have to organize for success, right, and establish their specifications and define their processes, get into some sort of LRIP, initial production, scale up and commercialize. So there's a huge set of challenges along that journey. And really, as Carpenter Additive, we wanted to pull together a number of different capabilities to help at all those different steps, right? And when we're talking about a program of this scale for an OEM, you know, this is a multiple year, multi-million dollars, right? And it means that at different points in this, a customer may be looking to in-source or outsource accordingly, okay? So what does that translate to? What does that translate to in terms of assets that Carpenter Additive has and capabilities that Carpenter Additive has? Well, in terms of R&D, we have 4 AM R&D centers with a full range of additive manufacturing or metal additive manufacturing equipment. Over 40 R&D and project management staff from both industry and academia who are able to support our customers and work on our either projects for the development of our own IP or materials, all the way through to specific customer consultative programs. In terms of raw material production and supply chain, we have capability to manufacture a full range of powders. We have 7 powder atomization locations and one of the world's largest gas atomizers. We are one of the world's largest gas atomizers in the world, and capability to manufacture, you know, titanium wire feedstock also. Then in terms of production of AM components, we have a NADCAP and AS9100 certified manufacturing facility in California, where we work on both LRIP and scale programs. And then the final thing I want to talk about is on the right-hand side, you can see a picture of our new emerging technology center, which really caps off $200 million of investment in additive manufacturing by Carpenter Technology today. And so within the Emerging Technology Center, we have a number of different AM platforms. We have machining, we have HIP capabilities, we have heat treatment capabilities, and we have our Customer Experience Center that you can see in the middle at the top. And this is really about, you know, working with our customers, working with our partners, and providing a scalable platform for end-to-end manufacturing all under one roof, right? We see it as really important that that total process is under one roof, so we can start to gather the data and the knowledge and really look at this process holistically rather than the individual components. Okay, so now I'm going to move on a little bit to talk about some of the challenges that we face, right? And one of the major challenges that we face within additive manufacturing is maximizing the use of materials. So a really brief introduction for those of you that don't know. But the chemistry of the powder changes as we use it. So if you look at oxygen content in powder, for example, the image on the left-hand side, this one here, shows the oxygen content in parts per million going up with the number of uses, right? which is then reflected in the parts that we build. So we have the oxygen content increasing in the part, and then it results in your altered mechanical properties. So here, this is an example with a nickel alloy, okay? And what we can see here is we can see that the fatigue life is reducing with the oxygen content, okay? So what that means is we have to develop new starting points for materials. So that might mean improved crack susceptibility in nickel alloys. It might mean higher strength stainless steels. It might mean increased fatigue performance for Ti-64, or it might mean cobalt-free materials, right? And so today what I'm going to talk about is I'm going to talk about Ti-64. So here's another example. So we've got the technical challenge of meeting mechanical properties, but we've also got the economics challenge. And so this example shows if you have a part in production, right? So you want to make 1,000 parts per year. If you've got 10 parts per build and 100 parts, that means you've got to do 100 builds per year. Okay, if your part is 1.6 kilos, it means that you fill up your machine with 160 kilos, you'll build 16 kilos of parts, and you have 144 kilos remaining. Now, if you're in a scenario where you can only use that powder once, you know, 0 reuses, which, by the way, we have customers qualified today, mainly for space, but we have customers who have qualified production components where they only allow, you know, the material to be used once. And it's not at this scale, but at this scale, it would result in us wasting $17 million of powder over a 5-year product life cycle, a 15-year product life cycle. If you then say, okay, what happens if we reuse it 15 times? That 17 million drops to 1.1 million. So, you know, what you're talking about is in a relatively small production scenario, you're saving $1 million a year by increasing reuse. And I understand this is an extreme example, but you can think the same thing from going from 10 to 20 recycles or 15 to 30 recycles. We have to understand exactly what we can do with our materials. Okay, so what affects this degradation? Well, so the videos you can see on the screen are showing an amount of disturbance caused by the laser melting a weld track, right? So you have the powder round being ejected or moved. You also have a number of other phenomena that going on there that we can talk about. So one of the things that we see, okay, is that as the laser is forming the melt pool, you're having these particles ejected out, and it's either molten particles ejecting out, which are absorbing oxygen and nitrogen, other gases onto the surface, because when they're molten, they absorb at a higher rate, and landing back in the powder bed. Okay. What we also have is we have in the melt pool itself at temperature is more susceptible to absorbing oxygen. Okay, so we see an increase in parts with laser. And the reality of it is when we talk about reuses, that's not really a great measurement, because as you increase the scan area, you have more spatter. If you have more spatter, you increase your oxygen and nitrogen. The second mechanism that we see is a heat affected zone. So the powder surrounding the part, we see oxygen pick up there, because although it's not being heated up to a temperature that makes it, melting temperature, it's heating up enough to start absorbing oxygen out of the atmosphere. And even if you have a really low level of oxygen inside your machine, you're still going to see some level of pickup and some level of degradation. And what this slide is demonstrating is that, okay, scan area, so more or less parts, is going to impact your amount of powder that's in your heat affected zone, as well as the size of your parts, right, and the latent heat that's in them. Okay, so when we look at the powder, okay, you can see some of these particles that are impacted. So we see misshapen particles, okay, which are still small enough that they make it through the recycling process, but they've significantly oxidized, and we see these heat affected zone particles that are still very spherical but have oxidized. Okay, so really important to be able to identify how much degradation you're seeing by taking real measurements, not by characterizing as once used, twice used, three uses. We use that as we talk about that terminology a lot, but it's because it's a simple way that people can understand it. But the reality of it is that every application and every production scenario will have different degradation rates. So in this specific degradation, we were looking at grade 23 Ti64, and we were really trying to determine the relationship between build cycle and oxygen, nitrogen, hydrogen concentration and mechanical properties. Now, I haven't put the whole study into this presentation today, but please reach out if you want to speak to some of our team about this, or get involved with a degradation study yourselves, right? We have teams who are available and capable of supporting. What I wanted to talk to you about was the two typical methods that people use for powder recycling. Okay, so the first one is top up, and this is where used powder from the previous build is you add some virgin powder to it to meet the required volume, and you continue until the virgin powder runs out. So you might have a large master batch that you're topping up from. And the second methodology is single batch. So this is where we complete builds successively until the entire batch of virgin material is processed. So once it's processed, all that exposed powder is sieved and blended, and it's put back into the machine. So you might fill up a build hopper, you might do 3 builds before you take that whole batch out, recycle it, and put that whole batch in, and then that's one exposure of powder. Okay. So we were focusing on medical applicable alloys of Ti64, so grade 23, and we used a true print at the LPW UK facility. So this top up ran for 30 builds, and both studies used the same build layout that you can see on the right hand side of the screen. We put in an oxygen limit set point, right, of 1000 ppm, but clearly that changes over the time of the build process as well. So here's the flow charts that show the top up and the single batch methodology. The real change in the first one being that after you've completed the build cycle, you blend in the used powder with some virgin powder to reload into the machine, whereas in the single batch, like we talked about before, you just recycle the exposed powder with no additions of powder until you don't have enough powder left to do the build. So the first result that we're showing here is the oxygen content in the powder. So what you can see is the blue line shows the single batch method, and the top up method is shown on this black line here. And what you can see is a much sharper increase in the single batch method than the top up method. So roughly what we're talking about here is we're talking about, almost double or almost twice the amount of oxygen pickup, and an increased rate on the single batch. It's tough to see here, but the gradient of this line is actually steeper than this line. Okay. So then when we look at what happens to the oxygen content in the parts, it's a similar story, almost double, not quite in this scenario. But what we see is us reaching a sort of equilibrium state with the top up methodology in terms of the oxygen content in parts, which is really quite interesting, because it means that typically people wouldn't be using grade 23 powder to build grade 23 parts, but in the medical industry that is often the specification. Aerospace, it may mean that using this grade 23 powder here gives you a much longer life making grade 5 parts. So it's very interesting. And ultimately what we're showing when we talk about this is that, you know, there's a huge amount of impact, not just in the machine, and not just in the original powder spec, but how people use it. And having control over that means that we require solutions. Now, this is in a controlled lab environment on one machine. Now, imagine the scale of that variation when you start to talk about 100 machines in production, right? It starts to get really complicated. The storage conditions of the powder start to have an impact, and, you know, and ultimately the environmental conditions of the manufacturing facility. So, you know, we really have to think about what tools and techniques we can put in place to keep us technically sound. And then from an economic standpoint, you know, when you start to think about, okay, well, does cheaper powder mean cheaper parts, right? We're seeing the productivity of these machines increasing, and really what we're seeing is that, you know, powder is becoming a bigger chunk of the cost of parts. But in this scenario, right, and this is an illustration for a nickel alloy, okay, if you paid $60 a kilo, for example, for a 200 parts per million oxygen, let's say you could get 15 reuses out of it, that would equate to a $30 per part in the scenario that we've got here. Whereas if you paid $70 a kilo for 100 parts per million oxygen, it would enable you, with this rate of oxygen pickup, to get 45 reuses, meaning your cost per part from the powder would be $12. Okay, so huge potential economic benefits of increasing powder reuse. And so what we've developed at Carpenter Additive is we've developed a solution that we call Powder Life, right, which is a closed loop powder handling solution. And it's made possible through the integration of multiple components, right? So we have pre-charged hoppers. So hoppers arriving at our customers full of powder ready to be loaded straight into their machine. We have tools and equipment to be able to load the powder into the machine, tools and equipment to be able to add virgin material for people using a top-up strategy, and sieve, blend, requalify the materials, right? So we're addressing, with this solution, with both hardware and software, we're addressing all the critical variables in a closed loop environment. So now let's talk a little bit about, so now let's talk a little bit about the material properties, right? So what this data here is showing is it's showing multiple years of titanium tensile data, okay? And what we can see is that, look, this was 2012, right? 2012, 2013, 14, 15, 16, 17, 18-ish time frame, right? We've had to anonymize the data. But what we're seeing here is in the early days, using a broader spec for our titanium 6-4 powder, we had quite a large scatter of our results of AM printed parts, right? Then what you can see is that as we iterated and put process controls in place, we started to reduce some of the number of outliers that we saw, right? And then here, this is where we introduced our grade 5+ titanium material. And what you can see is that there's a jump up in your yield stress in the material. So what that enables is it enables us to have the confidence to recycle the material more should we wish to. And this is the specification that we have for our grade 5+ material. And really our goal was to maximize our recyclability and strength while minimizing cracks on complex geometries. So this is a really, really tight chemistry. And it means that you can start with a lower oxygen powder and not have concerns about meeting the strength requirements. So therefore you get this longer recycles. And so what I wanted to show you was I wanted to just show you a bit of data from electron beam powder fusion. So this is the build layout. So what you can see here is there's 25 tensile bars, and so we keep the same line length in X and Y, we will put sacrificial parts in the build. Okay, that helps keep our standard deviation low. So there's two sets of results that I'm going to show here. The first set of results is in a pre-hip condition. And so what you'll see here is, you'll see, and I wanted to list all the results out, right? Rather than just showing an average and a standard deviation, I wanted to list all the results out to show you how small the amount of scatter is in these results, right? Across the build envelope. And so this is on an RCAM A2X, and you can see that your UTS, your ultimate tensile strength, you have a standard deviation of 1, right? KSI. Similarly, for a post-hip condition, right, you reduce that even further to a UTS of 0.7 and an elongation of 0.9. So really impressive in terms of, across the build. And then for a Q20, okay, so this shows the build layout. There's 27 Z-axis tensiles, 12 XY-axis tensiles, and here are all the results. And again, showing our ultimate tensile strength with a standard deviation of 1.1 and an elongation of 0.9. So what we're showing in that is that, we're translating these developments in materials through to repeatability in material characteristics and material properties. And I think that's really important, and especially when we're at such early stages with these technologies, right? We're using standard materials, but in future we're going to look to new materials, and having this good baseline of understanding of what happens with the material is critical. So in summary, Carpenter Additive has the near-term capabilities and the long-term plans to become your preferred AM partner. A bit of a sales pitch, but really those 130 years of materials expertise we see being incredibly valuable to the AM industry, and we hope that we can be providing solutions to you and be a partner in the long term. The last thing I want to say is, obviously, with everything that's going on at the moment, a reminder: wash your hands, don't touch your face, practice social distancing wherever you are in the world. Thank you very much.
Thank you, Ben. So we have about 2 minutes left until the next presentation, if we want to answer just maybe one question from the Q&A. All right. So is there one specific you would like to answer?
Sorry, I'm just trying to find how I get to. Okay, so I'm going to just read the first one that I see. So how big is the influence of different AM machines on the shown results? It's huge. Okay, so different AM machines have the capability to run at different oxygen contents. Different AM machines have different fundamental scan strategies, which means they have different levels of spatter. So it really is huge. And so that's why when we look at a scenario that we showed, right, it is dependent not only on geometry, on material, on machine, but also all the processes that you have within your supply chain. So yeah, super important. You're back.
Sorry, I exited out.
I answered all the questions.
Awesome. Well, thank you so much, Ben. It was a great presentation. Thank you for joining, and I hope you can stay to network in a little while as well.
Yeah, thanks. I will. I'll be online, and I'll make note of the questions and answer them individually.
Perfect.
Okay.
Thank you, Ben.
Thank you very much.
Thank you.